Welcome back, and today we're going to look at gravimetric analysis, which is one of the applications of stoichiometric calculations that we need to know about, where we can detect the amount of an analyte using precipitation reactions and stoichiometry to work out the mass of a substance. So gravimetric analysis is a quantitative technique, so we can get numerical data that combines us using solubility rules in order to have a knowledge of what precipitates will form in precipitation reactions, and then mass stoichiometry to work back to find out the mass of something that was present in our sample. So we're going to combine all of these, which means you do need to refresh your memory on the solubility rules. And of course, ionic equations of precipitation reactions are going to be critical for this. When we select the compound we want to know about, we have to separate it out from a sample mixture by precipitation and then weigh it. That's essentially what we're doing with gravimetric analysis. We have a compound that we want to know about, say sulfates in fertilizer or things like that. And then in order to separate it out from the other things it might be in a mixture, we can precipitate it out, collect the precipitate, and then get a mass for that compound and work backwards from there. So once we have the weight, we can look at the mass of the original sample and work out a percentage by mass of that particular thing in the mixture. So we do this for many things. You can do it for testing for the amount of salt in food, sulfates in water, so where we use different things to work out how much might be there and determine if they're in safe levels or not. So there's a set procedure for gravimetric analysis. So we usually have, if we're doing a water sample, which is relevant to Unit 2, we'll have a sample of water and then a solution of what we refer to as the precipitating agent. Okay, this precipitating agent is the solution that is going to form a precipitate with the analyte or the thing that we're looking for in the sample. Once we do that, a precipitate will form. We take our solution and we filter it through a sintered glass funnel or a Gooch crucible, which is a porcelain crucible like what you use for the magnesium oxide prac, but has holes in the bottom to allow the solution through and for us to just collect the precipitate. This is usually done with vacuum filtration because it can take quite a long time. So we dissolve the sample mixture into water, okay, or if we have water from a test site, we treat it with a chemical that will form a precipitate with the substance of interest, okay, so this is where our solubility rules come in into selecting the right kind of precipitating solution. The precipitate is then collected, usually by filtration, dried and weighed. Then we take the final mass and the original mass of the sample and work out how much of what we were looking for is in our solution. Let's have a look at how this works. So one of the ways this works is for being able to test the amount of sodium chloride in food. Now we know that sodium doesn't form any precipitates, chloride ions will. And because we know the stoichiometric ratio between sodium and chloride, we can then use that to work out how much salt was there. So food regulations limit the amount of salt in baby foods to 0.3% or below. So if we wanted to determine how much salt was in a sample of baby food, the first thing to do would be to take our baby food and weigh a portion of it in a sample. We would then dissolve that baby food in water, okay? And here there's often an additional filtration step because we may have to filter the non-soluble bits. So if we're looking at things like food, that would be fiber and things like that, and the chunky bits. So we would filter that out because we know that the sodium chloride is going to be soluble in the water, and any solids left behind aren't going to have the salt that we're after. We will then add an excess of a chemical to the baby food that will cause precipitation. And by excess, we need more than we need. So this will cause us to form, if we add AgNO3, of course, silver will react with chloride to form a precipitate of silver chloride. Okay, so we're adding AgNO3, silver nitrate, to our solution that we know contains our sodium chloride. We filter our solution to collect the sodium chloride, okay, and then we wash the precipitate with a small volume of water. Typically, we want this to be cold water, and we want to use as little as possible, because if we use a lot, remembering that solubility is a scale and most things are partially soluble, the more water we use, the more chance we have of washing away some of the precipitate that we were wanting to collect. Then the last thing is to dry this and repeat the drying at a temperature higher than the boiling point of water until a constant mass is obtained. And this means that the mass isn't changing each time we're putting it into the oven. So we can be certain that the water has all been driven from the sample. We know then that because we have NaCl aqueous reacting with AgNO3 aqueous to produce AgCl solid and NaNO3, that this is a 1:1 ratio. So if I can work out the number of mole of sodium chloride that was precipitated out, that will directly equal the number of mole of sodium chloride, sorry, silver chloride and sodium chloride, that was in the food sample at the start. So then we can take this, work out the mass of sodium chloride, and divide by the mass of the baby food to work out the percentage that was sodium chloride. So this is the whole idea behind gravimetric analysis and our ability to be able to detect something using precipitation reactions and quantify that. So the method, we need to be able to storyboard these and understand what's going on. So remember, we have a solid that has a soluble salt that we want to investigate. In this case, it's lead 2+. We dissolve that up and we have a mixture of our lead 2+ that we're wanting to investigate and a bunch of other things. If in this case we add something like a sulfate solution, okay, so sodium sulfate or something like that, lead will form a precipitate with the sulfate and the other components will remain in solution. So we need to choose a precipitating solution that will only precipitate out what we want. Otherwise, we take the risk of other ions adding to our mass and adding in an error. Then we can filter the precipitate, dry it, and work out the amount of lead sulfate, and then go back and work out how much lead was in the original sample. So gravimetric analysis isn't suitable for everything. It's only going to work on salts that form a stable precipitate or a stable salt with low solubility. Okay, so if it's got a high or a medium solubility, it's not going to work because with all the washing steps involved, we're going to wash our precipitate away and not get an accurate mass. So we can work out the amount of water present in a sample. This goes the opposite way. In this case, we would take the mass of something, we would dry it and dry to constant mass, okay? So this would be making sure that we recorded the mass at least probably around 3 times to make sure that the mass wasn't changing each time, to ensure that we'd gotten all the moisture out of the sample. And then we can have the mass initially and the mass final, okay, and they're going to have gotten smaller to work out the mass of water lost. Okay, so this is basically just drying something to figure out how much water has been lost from the sample. And of course, we can use it for metal ions present in a sample. A lot of our metal ions will form precipitates, okay, but they have to form precipitate. So it's certainly not going to be something that we can work out the amount of potassium or something like that because they're not going to form precipitates. But things that will form precipitates, such as lead, it's a really good process for doing to work out the amount of lead in a sample. We can also use it to detect the presence of anions. Okay, so if we want to find sulfates or phosphates, we can also use the right precipitating agent by adding in metal cations to get the precipitate and measure it from there. So of course, this means our solubility rules are critical when designing a gravimetric procedure. okay, because we have to be able to select the right precipitating agent and know whether or not we'll be able to collect a precipitate. So with the precipitate that we formed, it should have a known formula. It's going to be no use to us if we don't know the ratio and the formula of which the compound will form. Low solubility, be stabled when heated, because if it's not, we're not going to be able to dry it out properly. And then there's no good. If it's going to decompose as we heat it, we're not going to get an accurate final mass. And then the other thing is it needs to not form precipitates with other ions that are likely to be present. We want to try and have a selective precipitating agent that's only going to precipitate out what we're after. So your sodium, potassium, ammonium, nitrate, and ethanoates are highly soluble, so they're not going to form precipitates, so that's not going to work. Remembering that we have the mnemonic CHOPS for insoluble and spanner for soluble ions. You need to be able to write full, balanced, and ionic equations in order to be able to complete the questions for these. You are not usually given the equations or expected to be able to put them together yourself. So if this is something that you still need some help with, call out so we can get it sorted. Okay, let's have a look. This means that this is our general procedure for gravimetric analysis. We take our solid sample, we can grind it up, dissolve it up, then we mix to make sure we've dissolved as much as possible, filter out any solid particulates that are going to interfere with our analysis. Then we can add our precipitating agent. Okay, so once we've dried and worked it out, we can work out the mass of the sample, the concentration, and go from there. Let's see what it looks like in some actual calculations. With this, we need to remember that we're going to, for the mass precipitate, work out the number of mole of precipitate, then use stoichiometry to work out the number of mole of the substance, the unknown substance X, from our balanced equation, work out the mass that would have been in our original sample, and then work out a percentage mass from there. This means that there are significant sources of error in a gravimetric analysis. Okay, if we don't completely precipitate from the solution, we will end up with a lower percentage mass than actual, because we won't have gotten all the analyte that we were looking for out of solution. If the precipitate is not dried to a constant mass and there is still water around, we will have a higher than actual value, which could result in us having a percentage above 100% because the water is adding to the mass. Then, of course, if there are other ions in the sample also precipitating out with our analyte, which we try and avoid, but it's not always possible, we're going to also have a higher than actual value. Remembering that you can be asked questions about errors and what effect they would have on your final result. So it's important to be aware of these. Of course, we're going to be using our mole formulas, so N is equal to M on MR when we're doing this, remembering that our mass must always be in grams. We will have the number of mole, and then the formula mass or the molar mass is going to be obtained from our periodic table in grams per mole. Primarily, these will be the calculations that we're looking at because we're weighing the mass of precipitate. But of course, you may also need to use your concentration is equal to N on V, depending on if you're given the concentration of the solution as well. So this is worked example from your textbook, okay? And we're told, just like the one before, we're looking at food. Silver chloride precipitate is collected from a 7.802 gram sample of peanut butter, okay, and has a mass of 0.112 grams. What is the percentage of sodium chloride? So in this case, we have been given the mass of the precipitate, which is silver chloride. We have the mass of the sample, and we need to work out the percentage of sodium chloride. First things first, we need a balanced equation. So sodium chloride plus silver nitrate is going to produce silver chloride and silver nitrate. So we can see here that we have a 1:1 ratio between silver chloride and sodium chloride. We take the mass of the precipitate and divide by the molar mass of silver chloride. then that gives us the number of mole of the precipitate that was received in the analysis. Okay, we can see that it's a 1:1 ratio. So we can write out that relationship that the number of mole of sodium chloride is equal to the number of mole of silver chloride, which is the value that we calculated initially of 0.000781. Okay, from this, we can now work out the mass of sodium chloride. We're going to use our mass is equal to the number of mole multiplied by our molar mass. The molar mass being the sum of sodium and chlorine from the periodic table, which is 58.5, which gives us a 0.0457 grams of sodium chloride present from the original sample. This is the mass of sodium chloride, so we're going to take that and divide by the mass of the original sample, which is the total amount of sample that we had, multiply by 100 and get a 0.586% of sodium chloride per in this sample of peanut butter. Okay, so the peanut butter is going to have 0.586% of sodium chloride, which means that it would be outside of the regulations for baby food that we saw earlier. What I want you to do now is to actually try the next question yourself. Okay, so and have a go at storyboarding what's going on. This will help you visualize the reaction and get a better idea. Then I want you to come back and check the solution. Okay, so I've drawn my storyboard here for what's going on. We have the water sample from the question. That's 50 grams of a sample of water containing silver ions. We're adding potassium chromate to precipitate out the silver, forming Ag2CrO4. That is then filtered, heat is added, and time, so it's dried, and 1.32 grams of the precipitate is obtained. I've then written a balanced equation to say that 2 silver nitrate plus K2CrO4 is going to form Ag2CrO4 and 2 potassium nitrate solution. And now we're at the stage where this is my precipitate. I know the mass of this, which is 1.32 grams, and we're given the molar mass in the question, which means I can work out my number of mole by taking my 1.32 grams of precipitate and dividing by 331.7, which is the molar mass. And that will give me the number of mole of the precipitate that we obtained in the analysis, which is going to be 0.0039795 mole. Now I'm up to working out, so now I know this bit and I want to work out how much silver nitrate or silver was in the sample. So this means that I now need to write my mole ratio between the silver chromate precipitate and the silver nitrate over here. And what we can see, the N of silver nitrate, I'm going to use is equal to a ratio of what I want over what I've got, what I know, multiplied by the mole of Ag2CrO4. So this is going to equal 2 times 0.0039795, which is going to give us 0.00796 mole. Okay, so now I've worked out the number of mole of silver nitrate. Number of mole of silver is equal to the number of mole of silver nitrate, because the question asked me for the percentage of silver, percentage mass of silver in the water supply. So it's the silver specifically that we want to be looking for. So in this case, that means now that I can work out the mass of silver ions that were present in the sample by going the mass of Ag plus is going to equal the number of mole multiplied by the molar mass, which is going to be 0.00796 multiplied by checking my periodic table, and silver is 107.9, which is going to give us 0.859 grams of silver in the 50 gram sample. So now the percentage of silver is going to equal 0.859 divided by 50 multiplied by 100 over 1, and our final percentage is going to be 1.71%. So in this wastewater from the mining manufacturer, there is going to be 1.71% silver ions in that water sample. Okay, so that is how we can use gravimetric analysis to determine the amount of something in a sample using the mass of the precipitate. Here's another question for you to try. Okay, this is the same as the one that we did before, where you had to look at the mass of sodium chloride found in a food sample. Okay, so I want you to have a go at doing this and then come back, draw your own storyboard and come back and check the answer. So hopefully you were able to follow the procedures from earlier and you worked out that the percentage of sodium chloride in this food, in the cereal, is 0.586%. So there are some drawbacks to gravimetric analysis and major sources of error, and we started to discuss these before. But gravimetric analysis assumes that the substance being tested for is the only one that dissolves or does not dissolve in the solvent. Okay, so this is a fundamental assumption, and you will sometimes see questions where it says, what is the basic assumption of gravimetric analysis? And the basic assumption is that the precipitate that forms is only containing the ions that you intended, okay, that there isn't something else precipitating out with it. There are issues with the loss of substance through multiple transfer steps. So if we're having to dissolve and filter and then precipitate and filter and then transfer to a drying dish, all those transfer steps mean that we may have loss of mass, which could decrease our overall percentage. If incomplete drying occurs, it isn't dried to constant mass. There could be residual water, which adds to our final mass, increasing our percentage composition because the mass is higher than expected, or not precipitating out all of the substance, so not adding an excess of the precipitating agent. This can be avoided by testing the filtrate to see if you're still getting things out of solution. So another example question for you, okay? So a Gooch crucible is a filter crucible that we use that can also be put into an oven to dry. So this allows us to reduce one of those transfer steps. Okay, so this time we're looking at a nickel alloy being dissolved in acid and then being precipitated out. Okay, the mass of the alloy, so this is our sample mass, was recorded. The mass of the Gooch crucible was recorded. Then they have done a precipitate plus the Gooch crucible, and we can see that these two are concordant. Okay, so we have reached constant mass. Okay, so in this case, we would take the mass, the average of these, so we're going to have 23.65, and you're going to subtract the mass of the crucible. Okay, 23.650 minus 23.515 means that the mass of the precipitate is going to be the difference, okay? Because the precipitate is sitting inside the crucible, we don't want to add the mass of the crucible to it, otherwise we're going to have a very large percentage. Okay, so a mass of our precipitate is 0.135 grams. Okay, so now you need to calculate the percentage mass by mass of nickel in the alloy. Okay, explain why the mass of the precipitate changed from the first to the second weighing, and how could your result be for part A be affected if only one weighing had been made. So hopefully you had a go at this and you were able to work out that the percentage of nickel was 26.9%. Of course, this was worked out by taking the mass of the precipitate, dividing by the molar mass of the formula for that, which was given in the question. So you had to add all that up together and come up with 288.7 grams per mole. and then dividing by the mass of the original sample to get our percentage. For B, it says explain why the mass of the precipitate changed from the first to the second weighing. This is, of course, because in the drying process, water has been driven from the sample. It's dried, so the moisture has decreased, the meaning the mass has decreased. If we were to have used the first weighing measurement, there would have still been water in the sample, so the mass would have been higher, leading to a higher calculated percentage of nickel in the alloy. Okay, one last question for you to have a go at. I'm not going to step through this one step by step. Pause, have a go at the question, and then come back to see the solution. So here's the working for that question. We're working out the amount of chlorine present in DDT, which is an old pesticide, which is no longer used anymore because of chronic health conditions. So DDT contains 5 chlorine atoms. So the big one here is to remember that your mole ratio, you will have 5 times in here. So the number of mole of silver chloride is going to equal 5 times that of DDT. Okay, so we need to account for that in our ratio. Hopefully you picked that one up. So now it's your turn to have a bit more practice with these. Okay, so I recommend you do key questions 1 to 8 in your textbook, and then you can access these worksheets as well for extra practice. That'll give you lots of practice with mole calculations, as well as talking about the experimental errors and the ways in which gravimetric analysis is used. And I'll see you in class.